now we'll be discussing the second category of amino acid, and it is on the basis of functional group. So on the basis of functional group, we'll be seeing a second category of amino acids. So now we know that amino acids have two functional groups, that is the amino and the acid one. So they can be categorized into three categories. And now on the basis of functional group amino acids, the first category that comes is neutral amino acids. So as the name suggests, neutral meaning that the number of amino groups and the number of acid groups will be the same. So if we are to represent, so we have the number of NH2 becomes equal to the number of COOH. And a better way to represent it, let us just represent the number of NH2 by small n, and these two are equal. So a good example would be where NH2 is equal to COOH, that is the carboxylic acid group. So we can very easily see that here we have one NH2 and we have one COOH. So we have the number of NH2 which is equal to the number of COOH. The second category which comes to our mind is, what if the number of NH2 are greater than the number of COH? So of course NH2 being basic in nature will give rise to basic category of amino acids, where if we represent it with numbers, NH2, that is the number of NH2 will be greater than the number of carboxylic acid. Example would be where NH2 are more as compared to carboxylic acid. So let us take a very hypothetical example, and if we are to see this particular example over here, CHNH2, CH2, COOH. So here we can see that we have one COOH group and we have got two NH2 groups. So here we have n number of NH2 groups more than the number of COOH groups. So this is the second category of amino acid under the heading of functional group. Now the third category, if we have acidic, we can also have acidic too. So if we have basic, we can have acidic amino acids, and in acidic amino acid, the acid will be more, so the number of NH2 will be less than the number of COOH group, and thus they are known as acidic amino acids. A good example would be if we have more number of COH groups. So consider a COH group on this side, a CH2 connected to a CH and an NH2, very important. If you have to declare it as an amino acid, it has to have an NH2 group, and then we have COOH group. Now in this particular, we can see that there is one NH2 group and we have one COH group over here and one COH group over here. So we have got two COH group and one NH2 group, and of course the number of COH are greater than NH2, and thus it becomes acidic. So we have done three categories. One is the neutral, the second one is the basic, and the third one is of course the acidic. And this is all on the basis of functional groups. So now, seeing that the amino acid is very much dependent on its two functional group, we can say that the properties of amino acid is because of both NH2 and the COH group. So if we are to say that we know the dissociation constant of COH, the Ka, is approximately 10 raised to the power minus 5, and that of NH2, the Kb, is 10 raised to the power minus 5 again. So the amino acids here, because it is a combination of both COH as well as NH2, the K decreases, that is the dissociation constant decreases, and it is somewhere around 10 to the power minus 7 because it contains both the COH group and the NH2 group. So you just write a statement saying that dissociation constant dissociation constant is roughly equal in the 10 raised to the power minus 7 ranges due to the contribution of both NH2 and COOH group. Now, because both of them are contributing, so amino acids, the behavior is due to the presence of both acidic and the basic group on the same molecule. So what if I put this particular amino acid in an aqueous solution? So in aqueous solution, what happens is, so we'll be seeing behavior of amino acid in aqueous solution. So let us see that we have an amino acid, say NH2CH R alkyl group, and we have C double bond O H. C double bond OH. So we have got this amino acid. Now what happens is that in aqueous solution, the carboxyl group can lose a proton and amino acid, the amino group can accept a proton, which gives rise to a dipolar ion. So what am I talking about? So if in aqueous solution, two structures will be in equilibrium, and what are we trying to say? That the proton of COOH, that is this H, is lost and gets added to this place. So what structure arises is something of this sort, that NH3, the NH2 gets H plus, it gets an H plus, and the rest of the structure follows suit. So we have C double bond O, and since H positive is lost, we have got O negative. So we can see that we have got two charges over here, the positive charge and the negative charge respectively. And that is why we are calling this as a dipolar ion. And this particular dipolar ion is known as, it has got a name. This name is Zwitter ion. So it is called a Zwitter ion. So in aqueous solution, when we put an amino acid, there is a transfer of proton and a Zwitter ion is developed, also called as a dipolar ion. Let us write that name also. So dipolar ion. Okay, and here what happens is that this is a neutral species because it contains both positive. See, it contains both the positive and the negative charges, but it itself is a neutral species because here this NH3 positive is behaving as an acid because it has surplus of H plus, and the other C double bond O negative is behaving as a base because it is rich in electrons now. So this species as a whole is neutral. Please remember that. And we see this behavior of amino acid in aqueous solution. Now let us see some properties because of this Zwitter ion formation.